Uh, my name is Jassy. I'm a software mentor from Curtin FRC over in Western Australia, and today I'm going to be taking you through kind of the basics of computer vision and diving a little bit more into topics which you don't hear about a lot. It should be fun, so let's get started. I hope you can all see okay, but what makes a vision system? First, you have to get the image. That's called the acquisition stage. Then you have to think about that image a bit, and then you have to act on it. So let's dive into the first step. This is where everyone starts when they got to start thinking about vision tracking, and probably one of the most debated topics out of the three. First, you have the camera. This is the robot's eyes, what helps it see, just like your eyes. But just like your eyes, it can't see without any light. So you have to make it easier for the robot to see a bit, and this is where light selection comes into play. Some of you who haven't done vision processing before are probably thinking, why do I need a separate light when the field has lights already? And I'll get more into that in a bit. And then you have the processor, which is the robot's brain for vision, at least. This can be either your Robo Rio or something else, kind of like I'm sure many of you have seen a Raspberry Pi. So let's dive in. First, you have the camera choice. The two most common forms are the USB webcam and the network camera. Unless something's changed, I believe both of these come in your kit of parts every year, or at least in your rookie kit. And they each have their own drawbacks and advantages. So the USB webcam, it's very easy to find and purchase. If you don't have one in your kit of parts, you can get it just about any computer store. In fact, I think we have like 4 of that exact camera which you see in there. They're fairly widely supported as well, so any processor that you use it on, chances are it'll support it, but check. And it's typically much smaller form factor. The one in the image there is about, I don't know, 4 by 3 centimeters, something like that. So very, very, very small. You got to be careful though, they can be quite fragile as well. So make sure you either mount them correctly or get a stable one. Next up are the network cameras. These ones don't plug directly into your processor. They have their own little processor on board, but it can't do anything with the image. All it's there to do is take the image and send it over the network, in this case Ethernet. So they're typically more flexible to access. You can actually access them from multiple devices at once. So you can open it directly from your driver station as well as the coprocessor if you choose to. But they're also typically more expensive and might require extra hardware. That extra hardware being they need their own dedicated power supply a lot of the time. And you may also require a network switch to be able to use it and your coprocessor together at the same time, since a Robo Rio needs to have its own dedicated port on the wireless router. Moving on, we have the target. So this is what you're actually trying to find with your vision system. Fortunately, in FRC, these are really easy to find because they have this thing called retroreflective tape on them. If any of you have seen a high visibility jacket which construction workers use or something like that, those little grey strips, those are retroreflective as well. And there's also some on the moon, placed by Apollo 11, 14, and 15. These strips, unlike a mirror, as you can see down here, a mirror will reflect at an equal angle going away as it's coming in. A retroreflective surface reflects it straight back. This is great because if you're not 100% lined up with your target and you shine a light at it, that light's going to come right back with you, which is why if you've ever seen an image of a vision system on a field from the camera's point of view, you'll probably see that a lot of the targets are lit up in this like really, really bright green. That's what a retroreflector does. It just sends light right back, so it's really easy for you to tell where something is. Speaking of lights, light rings are commonly used to make these targets really easy to pick out, and this is the kind of image I was talking about in the last slide. This little light ring typically goes around the sensor of your camera, so that when it shoots light at the target, it bounces straight back and illuminates it in this super, super ugly green color, which is really, really easy to see. Why green? The basic reason is that when you're not looking at the field floor, not a whole lot is green. You see a lot of blue and red, partly because of the alliance stations. Stadium lights also might have a bit of a bluish red tinge to them, as well as human skin color has some undertones of red as well. So out of red, green, and blue, the best choice is green. This might change depending on the field though. If next year's field is this really, really ugly green color all over, probably not the best choice. Next, this is a bit of a footnote. I'll get back to this in a minute. But the Robo Rio, which is the main device which sits on site on board your robot, it can be a bit slow when processing large image streams. It can lag quite a bit, and it's also got a low amount of memory. And typically, you don't want this sort of thing running on the same processor as all your other critical code, like the thing that makes motors move and that kind of thing. Coprocessors can be a good option to kind of alleviate some of this stress. Very common ones are the Raspberry Pi and the NVIDIA Jetson, partly because Raspberry Pis are really easy to find and pretty cheap. And the NVIDIA Jetson you can actually get on first choice with a number of credits. I can't remember how many. Other good options are also the Pine 64, which now has a version called the Rock 64. These are quite good. You can actually do tracking in like 4K with these. We used them back in 2016 with our Connect. Or you can go the other route, which a lot of teams take, which is to use a phone, which has the advantage of having an inbuilt camera. And you can also communicate over this special kind of USB protocol with your RoboRio as well. I believe in 2016, Team 254 used a phone, and since it's become the new rage. They're pretty good, and they typically have all the software that you need already on them. And if you're a team who also does FTC, you might have a few phones left over, so it might be something worth trying. That camera, by the way, the Pine 64 and the Raspberry Pi also have these little camera boards which you can get, which connect to these little headers on the device, which you can use to add your own camera to them instead of buying another USB camera. The advantage of that is they don't require their own power. They're typically less bulky, plug straight into the board so you're not using up a USB port, and because of that, the lag is typically less. The NVIDIA Jetson is also a good choice because it's basically a GPU on a board. It is quite big though, so keep that in mind. One caveat of using a coprocessor is that you're going to have to maintain two code bases, one which runs on your main robot and one which runs on the coprocessor. This is typically good if you have a large programming team of more than a couple of people, but you also have to maintain that ability to communicate between them, which is something I'll get to later. Okay, I hope we're all good on the acquisition stage so far. There are some other options as well though. So far we've talked about the visible spectrum. You can actually go outside of a visible spectrum for the human eyes and into the visible spectrum for film and digital cameras. So I'm sure you've all heard of the Microsoft Kinect. It's this little sensor that the Xbox team came out with a couple of years ago, which could track your body. Now, the thing about this is it has two cameras here. One for red, green, blue, so color images, and then another one for infrared images. And then over on the other side, it has this little infrared projector, which sends out an array of infrared dots. The cool thing about this is, and this is the same technology used in night vision cameras, by the way, is that you can see just the infrared using that little infrared camera, which is what this image down here is. The retroreflective target sticks out like a sore thumb in this case, because you're seeing infrared light which really has no place elsewhere. Something to keep in mind though is if you read on a little bit, IR conflicts with outside light, so light coming from the sun. If you also have some kind of tinted material between your camera and your target, it won't be able to see it. Some stadium lights conflict with this, but given that almost all of you who are watching this or tuning into this are at the Sydney Olympic Theatre for our regionals, I can say with pretty good certainty that the Kinect works just fine there because we used it back in 2016. To give kind of a little bit of a demo of where this kind of sits, this range is where your eyes can see. and everything here is what your eyes can't see, in this case near infrared. Uh, this helps a lot because you don't have to look for this very specific green color, and the image is also monochrome, making it take up less space. So instead of one channel for red, green, and blue, you just have one channel for brightness, which also makes it a lot easier to deal with. It's a really effective way of dealing with it, and infrared light also falls off pretty well with distance. So as long as you don't have anything maybe like 2 inches in front of your camera, you're pretty much fine. Going into software, so the stuff that actually sits on the coprocessor or your rubber rail in that case, hardware doesn't function on its own. You do need a bit of software to make this happen. Basic software for interacting with your camera. There's a couple of ways to do it. So for getting the image out of the camera, CS Core, also previously known as Camera Server, it's maintained from the same guys who write WPI-lib for your rubber rail. It's a pretty good option. It can interact with both USB and network cameras, and it's also open source, so you can see pretty much everything. That being said, you can also use your own software backing stuff. So, for example, CS Core doesn't work with the Kinect, so we use something called libfreenect, which is another software package which you can run on your devices to make it interact with that specific kind of camera. That being said, it is open source. If you find something which is incompatible, you can always write it yourself and make sure that everyone else can use it. Moving along from the actual acquisition stage, you have something called GRIP, which is also maintained by WPI. And there was a great conference on this during championships last year, and I'm sure there's a few talks that you can find online. They're great for concept and design of your vision system. So this is an image of GRIP on the side here. You basically have your input stage, which is somewhere over here. And then as it goes along, you generate what's called a vision pipeline. And so you have the first step, the second step, the third step, and that's all represented by this stuff down here. It's very nice and graphical. If you want to go that route, it will also generate some code for you to use as well, but I can't vouch for how good that is because I haven't used it. But it is also an option if you're getting into it for the first year. Both of these are backed by something called OpenCV. OpenCV stands for Open Computer Vision, and it's this very popular library both in FRC and in the just general computer vision industry for processing images. I'll get more into this later, but all you need to know is that OpenCV is pretty much the best, if not the only option. And there's also binaries distributed for this, pre-built for the Raspberry Pi and Robo Rio and all that kind of stuff. In fact, it already lives inside of your robot code, but you might not know it. Moving on. If you have any questions, by the way, send them to one of the main people at the event and they'll type it through to me so I can answer it at some point. But hopefully everyone's all good on the acquisition stage so far. So once you got your image, you have to actually think about your image a bit. And it looks like a lengthy process, but it makes a lot of sense once you get into it. So first you have filtering, which is taking out large chunks, then processing, which is turning those chunks into something meaningful, then identifying which ones you want to keep, and then interpreting what that data means. So let's go ahead and work through it one by one. First up is filtering. This is reducing the big data to small data. So we're taking big, rough chunks out of the image as the initial step, all the garbage we don't care about. This is commonly done as a threshold. So you'll set for your criteria, which we'll get to in the next slide. You'll say anything below it, set to 0, which is a black pixel in this bottom image. Anything above or equal to it, set to a 1, which is a white pixel here. This creates a black and white image from your initial image. So in this case, we're saying care about anything that's green and like somewhat bright. So green in this case isn't too important because if you look up here, that's actually only a little bit green. It's very overexposed because what we're doing is with the light, which we saw in a previous step, we're shining a ton of light at the image, but the camera senses exposure can't quite handle it. Those of you who've done photography will probably know a bit more about this. Typically what it means is that you're flooding the image with light and you haven't set your exposure properly. So it kind of overexposes the sensor and kind of limits itself to the maximum value, which is white across all channels. This camera's exposure here has been lowered a bit, but it could be lower given how overexposed that is. Those of you, again, if you have some kind of grasp about photography, this will make a lot more sense. But to kind of give a bit of perspective, if you take your phone camera and point it at a very, very bright colored light, it'll appear as white because it's not exposed correctly. Moving on to filtering again. So this is basically to get rid of all the junk in the image, all the stuff that we don't care about. In this case, we're taking everything which is reasonably bright and not completely colorless. So we got a little bit of a hint of the Alliance Station lamp here, a little bit of reflection off of the driver station metal. The lights along the side of the tower, this is from 2016 Stronghold, by the way. As well as a little bit of reflection here, and of course the two targets that we actually care about, these little U shapes. There are two types of filtering which you probably want to be concerned with. The first is red, green, blue, and I'm sure you've all heard of RGB at some stage. This is the underlying technology which powers just about every image that you see on the internet. So you might think, okay, just take everything which is a fairly high green value since our light is green, and reject the others. The problem with that is that as you go towards white, all channels start to go towards 255, which is a maximum value. Which means, sure, my image can be mostly green, but if it's like a color like this, which I'm sure you'll all agree with me is indeed green, you can see red and blue are actually kind of high, so we can't really filter off green alone. If we reduced green here and kept red and blue at the same, it would go towards more of a blackish color. It would just get dim. So this is why red, green, blue isn't that great, because it's not very... There's no easy way to tell where on the color spectrum it lies. It's just how to tell how many of each of the colors are mixed together to make some other color, which is really hard to work backwards from. So it doesn't really give you a sense of where on the color spectrum it is, but it does give you a sense of brightness of each of those individual three, I say primary in air quotes here, colors. This is where HSV comes in, which is way, way more useful, and actually what we use in this last image here. HSV stands for hue, saturation, and value. You can think of value as how bright the image is, so 0 being black and the maximum value being white. Saturation is how much color, so for 0 it'll be no color, and all the way up at the maximum it'll be very, very saturated, a lot of color in there. And then hue is just where on the color spectrum it lies. This is a lot more useful. If you take a look down here, you can see hue is kind of like as you go outside the perimeter. Saturation is as you go inside out, so white to color. And then value is bottom to top, which is black to white. A combination of those will give you your color. The cool thing about this is that if I want to, for example, pick out a purple color, but I'm okay if it's a little bit reddish or a little bit bluish, I can do a range on that entire hue there, and then just keep my value and saturation colors, values where I want them otherwise. That's a great thing. You can pull out neighboring hues and bring them in, which is really, really useful, since pretty rarely you're going to get an exact color value for some single pixel on your image. So, both of these are the same color but represented in HSV and in RGB. So HSV is typically the more useful one. Diving into a bit of code for this, this is in C++ using the OpenCV library. For Java it's pretty similar. Basically I have the low and high values for my HSV reading, so anything which lands kind of between these values. So I have between 75 and 135 degrees, which is around this area here for green. You can find a chart which has all these values on them. And then saturation, I'm not too bothered. This here should actually be set to like 255, but this example is wrong. I'll fix that before I release the slides to you. And then the last one is value, which is how bright it is. So in this case, we're taking anything from about the halfway point up, which allows us to catch those darker colors. Then we do a color range. So this is converting RGB, which our image was captured in, to HSV. So I have to change the color space. This is coming from video in to video out. In this case, I'm using video out as a temporary in this stage. And this is a constant. This image is actually in BGR, not RGB, the other way around. So just keep that in mind. That's what most cameras will output. Moving on, we're taking that temporary value of video out. We're running in range, which is our thresholding function, and saying anything within these values set to 1, anything outside set to 0. And then we're shoving that out to video out. So that's the basic how to get from this to this. Okay, I hope everyone's pretty solid with that so far. Again, I'll release these slides at some point. Moving on, we have processing. So this is taking our smaller image, so we're taking smaller in terms of how much data there is, not how big that data is, not in terms of megabytes, but how much data we have to work in. So we're taking our smaller, more refined image and we're converting it to something we actually care about. This is taking the pixels and converting them to something which you can relate to something called features. So usually this is in the form of contours, which is a polygon encompassing a group of pixels. You can think of it just as a shape with an arbitrary amount of corners and points and with a random area and stuff like that. So in this case, it's going around the perimeter of all these white sections, and it's drawing a polygon around them. I've colored each individual one in this image, and then you also have some for the light strips, and it picked up a little bit of this alliance lamp up here, and a little bit of a reflection off the driver station, but we have found the 2 targets that we care about up here, and that's all that matters for now, because we can actually filter this. So moving on. These are the contours before the filter. These are something called convex hulls, which I'll get to in a minute. And these are the contours after the filter. Notice how it's got rid of all the junk, and all we care about are these 2 little targets up here, and it successfully found them, which makes our lives a whole lot easier going down the track. So we've essentially reduced our image from this to this, which is a pretty big step. So let's run through it nice and slow. The process contours that we have, so from this image here, can be filtered further based on a number of criteria, like their area, or how much of it is solid, or how wide it is compared to how high it is. Each of these will depend on properties of the object that you're looking for. So in this case, the targets from first stronghold. Hulls are these little things. You can think of them like contours, but all the angles inside of them are less than, well, they're all convex, so they completely encompass. What that means is that when you take a look, these images appear a bit low res, probably over Skype, so I'll switch back to this one. If you take a look at this, you've got this little U shape here. A convex hull is just going around, and it's basically filling in this missing area here. What this allows us to do is it allows us to determine something called solidity. So solidity is basically inside of that feature that we found, inside of that object, how much of it is solid compared to how much of it is not. So how much of it is filled in compared to how much of it is blank. So in the case of this image up here, of this little rectangle, how much of it is white compared to how much of it is black. This is really useful because if you have some targets which don't have this little gap in the middle, their solidity will be close to 100%. But in the case of this one, the solidity can be in a range of areas. We know it's probably not going to be less than some value, and we know that it's probably not going to be higher than some value. This is what convex hulls allows us to calculate. So it's the area of the contour, which is this, divided by the area of the overall hull. So how much of it is white, how much of it is solid. We can also filter based on just the areas of the contours themselves. so how big it is on the image. For example, we probably don't want this little dot here because it's tiny and insignificant and we don't care about it. And ratio of width to height is a number of other things that you can calculate it on, but these are typically the big three, which you'll see very, very often. So to get from here to here, this is the code that runs it. It looks very, very, very confusing, but it's very simple once I run through it with you. So first of all, we're taking a video in and we're pushing some form of filtered contours out. So the video that we're taking in is our filtered image here. So we call this after filter. Contours, each one is stored as a vector of points. A vector, in this case, you can think of being as a list. And then a vector of that gives us a collection of contours, so a list of contours, where each contour is a list of points. We run this really magic function called find contours. No one really knows what it does under the hood, but it just does it. That's a lie. You can look through it if you really want to. But we take our video in, we're going to clone it so that we leave the original video untouched, because this function can modify video in if it wants to, which typically you don't want to do. So we're cloning it, so we're copying it in memory from one place to another. Our output is going to be contours up here, and then these are just some arguments to say how we want to find the contours. In this case, we're only selecting external ones. What that means is that inside of these here, if they had little contours inside of them, so inside of their own little things, we're ignoring them. Next up, this argument here, which is just the algorithm that we use to find the contours. This is, for FRC terms, this is pretty much a constant. You don't have to worry about changing this value. So now we've got our contours, which is this image here, and now we want to filter them down into this image here. So we're going to go through all the contours. So we're going to iterate over that list. We're going to get the current contour, and we're going to find its convex hull. This convex hull is these images here, that little rectangular box around the contour, or rectangular-like. So we're taking it from the contour and we're shoving it in hull, which is also a vector of points. Next, we are going to do we're going to find the area of our contour, that's just contour area. And then the solidity, which is the area, which is the area of the contour divided by the area of the hull. Keep in mind that hulls are technically contours themselves, so you use the same function, but you can think of them as separate for pretty much everything else. So we got area and solidity, and moving on, this is our final condition to check if this contour fits within what we want it to fit in. So in this case, if it's got an area larger than 300, this is in terms of pixels. This number will change depending on how far away you want to see the target from, how big the target is, how the resolution of your camera, a number of variables. Moving on, we also have the solidity. So in this case, we're saying less than 75%. This number can probably be dropped down a bit for this specific target, but this makes it so that we can see the target from a range of angles, since there will be a bit of error in there. And also from further away, it might appear differently. But anyway, if it matches those two criteria, we're going to push it into the filtered contours vector, which goes back out to the caller of this function. Again, in Java, it's pretty similar, although you'll probably find most of these functions are called in a slightly different way, but the names of the functions will remain the same, and the basic logic as well. If you're doing your processing in some language like Python, read the manual, because I don't code in Python, but I'm pretty sure it's the same process. Anyway, I will post a code sample, which was actually our vision tracking code from 2016, which had all of this merged together. It might be a bit to take in, but I'll publish that at the conclusion of this. Moving on. So now that we've processed our data, so we converted it to something which we actually care about. So in this case, these two images, each of which is a contour. So the two targets that we found. we have to identify which one of these we want to use, because our robot isn't Schrodinger's cat. We can only align to one of them at a time. Which one do we choose? This is very, very dependent on the year and what your robot's capable of and what you're going for. But basically, if you find multiple targets, which one do you want to use? Do you want to use the first one that you found in the image, which in this case would be the left one, which in this case does appear slightly at a better angle of attack than the other one for most robots? The biggest one, so which one takes up the most area in the image, or some other criteria? In the case of Stronghold here, it might be the target which appears to have the closest to zero angle possible, so the one closest to your robot heading, or it might be the one with the highest width to height ratio, since as you start going across, perspective will shift that image so it appears less wide, but the height doesn't change. Again, this is very dependent on your year and what you want to go for. I've even heard of teams who just send all the targets back to the driver station and they ask the driver which one they want to select. There's really no wrong answer here. So experiment, prototype, come up with different ways to do it. That's my best advice. Next up, once we select the target that we want to use, we have to interpret that data in a way which the Roborio can understand or our code can understand. Contours are pretty useless on their own. They're just a collection of points, and without the backing library, in this case OpenCV, to kind of interpret them for you, they're pretty useless. So, requirements for this will change year to year, but typically almost all the time you want to find the center point of the target. In this case, it's this little pink dot in the middle. This can be done in a number of ways. So, a really good way to do it is to take a bounding box, which is this little purple outline, which is a rectangle, a pure rectangle of the outside with no rotation, and find the center point of it. You can then, if you really want to, you can also use the size of the target to try and determine how far away you are, but this is pretty rare. You don't need it a lot of the time. And then finally, you can actually draw a line in the center of your frame, assuming this is where your robot center is, and you can use some math, including the focal length of your camera, which you can find from its data sheet or by testing or something like that, and you can find how many degrees off it is, and then you can pass that data to your gyroscope and the rest of your drive code to automatically align to the center. Get more into this later. In this case, this is a pretty extreme case. The angle is about 4 degrees, so 4 degrees off of our robot's true heading. There's a lot of math which you can use for this, which you can find online or in other code samples. I won't be getting into it here because it depends on your camera, and sometimes you might not even want to find that center point. It's up to you. So this is kind of left as a bit of further reading, but you can do that with the focal length of your camera and how many pixels away from the center it is. Putting it all together, you get something which looks a little bit like this. So this is a demonstration of our vision system from 2016 using a Pine 64 and Connect, and this is the result. So you'll never see this in a match, but this is me holding up a high goal model on a piece of cardboard and spinning it around. And this is real time. So it's tracking it in 30 frames per second, which is about the same refresh rate as a normal USB webcam or most film cameras. And it's tracking just fine. No glitches so far. If you spin it around really fast, it'll even kind of compensate for the motion blur a bit, just because we put our boundary of what we want to capture a little bit loose. And yeah, we're also displaying it on my MacBook as well. So I was sending data over the network and getting it to there, but I'll get more into that later. So now we have some information that we actually care about. In this case, it might be the angle to your target or something like that. How do we act upon this? So how do we take this data and use it in some meaningful way for the robot? The first thing that jumps to a lot of people's heads is automatically aligning up to the target and taking a shot. in the case of 2016 or 2017, where it's a shooting game. Not necessarily. There are a number of ways to do it. So first of all, it's not necessarily automated. If you're people working on control on the robot, people working on the drivetrain, or the main shooter don't feel like they can do that automation, you actually don't need automation at all. So moving on, the quickest way to kind of act on this data is to just display it, sending it over to the driver station. So the simplest form of this is just displaying the data and letting the drivers use it to assist how they play the match. You can either display the entire image, which will be exactly what your camera sees in all colors and stuff like that. It gives a nice detailed view, but it can also be slow and laggy because you're limited by the network connection connecting your processor or your camera and your driver station. So you're relying on that Wi-Fi getting through the field network and then onto your driver station, which then has to render that image to see it, and it can be very, very slow. So for those of you who don't know, the field employs a 7 megabit per second bandwidth limit, which if any of you have tried to do vision tracking in the past, is not very lenient on how many images you can send over, so it will tend to cap you, which will reduce your frame rate down to something like 15 or 10, which is very, very stuttery and hard to control. Or you can just display the things that you care about. So, for example, you could send over just the contours, which are just a vector of points, of floating point numbers. Does not take a lot of bandwidth at all, which means that you can get that data out fast, you can process it, and you can display it fast on your driver station as well. The thing about this is that it is just the data you care about, so it lacks the detail of surrounding objects, like other robots or obstructions between you and your goal. But then again, your driver should also be looking at the field, so take what you will. In my case, I just send over, I don't even send the contours, I just send this bounding box around the target, since that's typically enough, and how many degrees off of the target we are. You can display these on the drive station in numerous ways when it comes to software. So you can use, for the full image, something like a shuffleboard, which is the 2018 version of Smart Dashboard, which was used in the past. The FRC driver station itself, you can actually render images in as well, especially if you're a LabVIEW team, this will come in quite handy. Or you can view it through web streaming. So many cameras, like the Axis network camera, will actually send out a raw bucket of images, sorry, which you can view on a web browser, which a lot of teams do also. You can also set this up with CS Core to make that happen as well, I believe. If you want to render just a partial image though, just for contours, you're probably going to have to roll your own solution. So this might include having your own bit of software. A third bit of software is separate from your vision processing and your robot control, which sits on your driver station, and its only job is to take in information about those contours or those bounding boxes or that filtered image or something like that and display it. You can also make this happen if you're particularly a savvy web developer, is you can also just display it inside of a little web page as well, which was our strategy for a couple of years. Both of these work just fine. Shuffleboard actually might be getting support for this at some point, but we're not sure. So you can probably roll your own solution for it if you really want to, or just send over the full image. For your first time doing it, you'll probably find that there's a lot of bumps in how you actually display this data, and it might drop out sometimes, and it'll be quite laggy, and it might not work all the time, but that's fine. So in future years, you have the opportunity to develop on that. And if you have a large programming team, this can just give people stuff to do when people are working on something else. And it's one of the rare parts of robot code where you actually get to see what's happening in a nice visual way. So it can be quite fun as well. Moving on. probably the holy grail of vision processing in FRC at least, is automated. So this is taking the output from your vision system to automatically do something on the robot, whether it be lining up to a goal, maybe taking a shot, following a moving target, or, well, a number of things. Depends on the game. I don't know what next year's game is. This year it might be aligning up to the airship to drop off a gear, or it might be aligning up to the boilers to take a shot, for example. There are a number of ways to do this, but it all kind of boils down to one thing, and this is called feedback. A feedback control system, also known as closed loop, as compared to what many of you have probably implemented in the past, which is open loop. It takes some input and does some action, so it gives some output, but also uses a result of that action as measured by a sensor or from its previous value or something like that, and it uses it to influence the next step in doing that input-output control. This allows it to have some knowledge about how it's doing. It's kind of like the difference between blindfolding yourself and going forward 10 meters, that's what you would call open loop, compared to opening your eyes and going 10 meters with a tape measure on the ground, because you can see how far you're going and you can correct for it as you go along. That's the key difference between open and closed loop. Most of your drive control is probably open loop, because you're taking input directly from a joystick and shoving it directly out to the motors, which is fine. But when your driver doesn't have eyes to make that happen, when the vision system is taking over, you have to have some kind of feedback to make it happen, in order to make it happen well, accurately. In this case, the code is open loop, but your driver's eyes kind of add that little feedback to itself. So let's use the camera as feedback. So we got a set point. In this case, it'll be 0 degrees. So this is a 0 degree difference between where the target is and where your robot's pointing. And we feed that into a PID controller, which you can think of as just something which tries to get to that set point by sending some output value to the drive code. You've probably heard of this before. It stands for Proportional Integral Derivative Controller. Not too important for this. That's a lecture for another time, like all in itself. But you can think of it as just something which tries to get to the set point based on some feedback. We shove that value, which the PID controller generates, into our drive code, which in turn sends it out to the motors. And then we use our vision system, which is seeing how that target changes over time, or seeing how it changes when we send that motor output out. And it's saying, okay, now I'm this amount of degrees off, and I send that into the PID controller. So if your vision system starts with 4 degrees away from the target, you feed that into the PID controller, but the PID controller wants to get to 0. So it sends out its own value to the drive code to try and correct for that. Then, once doing that on the next step of the loop, the vision system's like, oh, I'm only 3 degrees off now. It feeds that into the PID controller, and it goes all the way around until it gets to 0, and then it will hold that point. And the PID controller has its own little parameters, which you can tune to kind of make that happen. What's the problem here? So we have this whole thing. What's the problem? Why will this be inaccurate, and why will it kind of judder around the target a ton? The answer is probably not as simple as you think, but I'll give you a couple of moments to think about it. Okay, so let's dive back into it. So our vision system is getting that output and sending it back into the PID controller. The problem here is that you're limited by your camera's frame rate. You can't do the next step until the vision system gives some output. So you're limited to that 30 frames per second, 20 frames per second, 15 frames per second that your camera and vision system are operating at. And you're waiting on that to come from your coprocessor to your RoboRio if you're using 2 different processors. And you're waiting for your camera to get that image. You're waiting for all your logic to go in. And it's just very, very slow. 30 hertz, which is 30 times a second, might sound like a lot, but in terms of robot control, it's really not that much. The code which sends your joystick to your motors runs at 50. So 50 compared to 30, you're already slowing down what was already pretty slow in the grand scheme of things. To visualize this, this part of the loop is capable of running fast, so more than 50 Hertz, as fast as you want it, as fast as your code can possibly accommodate, but you're being limited to 30. So that's slowing down everything here because you have this feedback loop here. So what is the solution to this? Well, we want to remove that dependency on the camera. So one of the options is to get a faster camera, which is not very easy to do. Or you can use a different sensor to kind of fuse in with that vision system as well. Something like this. So we take our vision system, which is running in its own little loop at 30 Hertz or however many Hertz the camera runs at, and it's constantly updating the set point of the PID controller. So instead of a set point of 0, the set point is going to be the difference that we are away from our current angle and where we want to be based on some initial thing. That's a little bit of math, but basically it's constantly updating that set point based on where the camera thinks it is. And that happens at 30 Hertz. The PID controller then operates based on the feedback from a gyroscope. Now, gyroscopes are really, really fast at giving feedback. In most ones which you'll find in FRC, like the NavX or the RS540 or something that you find on some board like the Spartan board or whatever, they're all capable of running at like not even 50 Hertz, 100, 200, 300, 500, 1000 Hertz, and they're actually pretty accurate. So they're a lot better than a vision system for this kind of application. In this case, the set point, if we change the set point in some way, it doesn't matter all that much because it's calculated off of where the vision system thinks the target is relative to the field, not relative to the robot. This is done by taking the angle that it sees and adding it to the current gyro angle. So that runs in its own little loop. It keeps updating the PID controller so it can refine its guess over time. So it's a little bit more accurate. So when your motors have stopped, the camera might say, oh, we're still 1 degree, 0.5 of a degree off. Try to align a little bit better, and it'll try to correct for itself. That goes back into the drive code, into the motor outputs, and the feedback for the PID controller, so the error that it sees between where it wants to be and where it is all based off the gyro, which updates really fast and is almost instant in terms of when it gets data from the real world and pushes it out to RoboRio. In terms of how to kind of improve this, you can also include some other stuff like the vision system knowing how laggy it is, so knowing how long it takes to process a frame, knowing how long it takes that frame to go from the real world through the camera sensor to the code, how long it takes to go over the network and correcting for that. Many teams have done that in the past, and I believe the same people who make the NavX actually have a sensor fusion library which will do all this for you. SF2, I believe it's called. I believe some other teams like 254 have also used this in the past as well. You can also take some kind of error measurement from your gyro so you know how noisy your gyro is or how much it drifts over time or something like that. But that's kind of, again, that's another talk all on its own. So this is a bit of a better approach. You do have 2 loops running simultaneously. So you have a slow loop and then a fast loop. So this is the one which actually sends it out to your motors. But those 2 loops you can communicate between if you handle your code right. Again, there'll be a demonstration of this at some point. So, moving on from this, this is kind of just a text version of what I just read out. Using both the camera and the gyroscope is a very basic form of something called sensor fusion, which is taking 2 sensors or a group of sensors, or as many sensors as you want, and using them together to make a system which will be more accurate, less uncertain, and typically higher performance than any one of those sensors on its own. In this case, our two sensors are the camera and the gyroscope. You can use just the camera, but it's going to be the alignment's going to be very off because it just updates too slow. And if you just use the gyro, well, you don't know where the target is, right? So the camera gives us knowledge of our target relative to the robot, but it's pretty slow, less than 30 frames per second, also known as hertz. The camera may also have some of its own lag, which is pretty large, especially when you're using a coprocessor. The gyroscope knows where the robot is, but it has a little bit of uncertainty on its own. It has a little bit of noise, it'll drift over time just due to how gyros work, but also updates a lot faster than the camera and with a lot lower lag. So you can use the camera to constantly update where your target is, and the gyro to constantly update where your robot is. And those control loops work together to try and reach that 0-degree difference between where the target is and where you are. Again, if you have any questions about this, be sure to, I don't know, shout them out or something. The people at the event will give a bit of a better idea of what's going on. So putting this all together, we have our three main stages: the acquire stage, the thinking stage, and the acting stage. The acquire stage is where we take our camera and lights and our processor and put them all together. Processor isn't needed if you're just doing it on the RoboRio, or the processor and your camera can be one and the same if you're using something like a camera module for a Raspberry Pi, or if you're using a phone or something like that. Moving on to the thinking stage, this is what most people kind of instantly think about when they hear of computer vision. You have your filter, which takes out large chunks. You have your processing, which finds the features, in this case contours, and filters them out based on its own criteria to only the ones you care about. Then identify, which further narrows it down to which of those main features you really, really do care about, which one you want to select for your upcoming algorithm or whatever in acting. And then interpreting. So interpreting that data to convert to something meaningful, like how many degrees am I off from the target or something like that. Then you have acting, which you can either do displaying the data or automatic action, or preferably both. It's really up to you how much time you have in the build season. I would really, really, really support trying to do this before the build season, because you'll get such a leg up on yourself if you do some prototyping before build season rather than doing it like the day kickoff starts, because you'll spend 3 weeks wondering why your camera doesn't work. So I would really recommend doing this as soon as you can. Now's a good time even. This is a little bit of a footnote on coprocessors. So earlier I kind of discussed the usage of coprocessors like the Raspberry Pi or NVIDIA Jetson or Pine64 or a phone. All the steps so far have kind of been in one linear order: acquire, think, act, without any kind of reference to which one happens on the coprocessor and which one happens on your RoboRio. Generally speaking, and this is very general, you can kind of mix them in with each other or redo it depending on how confident you are or what you want to do. When you're using a coprocessor, we can handle these stages in separate kind of blocks instead of all in one. So we can do the acquisition and thinking on the coprocessor, which is getting the image and converting it to something meaningful. And then we can send that meaningful data over the network to the RoboRio to then act upon. This is pretty key. In this case, it would be taking your image, processing it down into how many degrees off of the target you are and maybe how far away you think you are from the target. And then just sending those values to the RoboRio to then do that kind of aligning with the target and stuff like that, since the RoboRio is the only device which has raw access to the motors and stuff like that. To do this communication between the coprocessor and the RoboRio, there are a number of ways that you can do it. Popular methods include sending over network tables, which is the backing network infrastructure of WPLib, and it's already on your RoboRio right now. Using something like protocol buffers, which were developed by Google. Well, the most popular implementation was developed by Google, which you can use also. Or you can just write your own data protocol. if you really, really want to get into that. Our data protocol back in 2016 was really easy. It was 5 numbers. So for each target, there would be 5 numbers. The ID, so which one in the frame it was, so either 0, 1, or if you saw all 3 targets at once, 2. How wide the target was, how high the target was, the X offset, so where it sit horizontally in the frame and where it sit vertically in the frame. Those were the only 5 values that we sent. That was extremely fast, but you might want more data, like the entire contour, in which case using something like network tables or protocol buffers might be a better option. Each of these has its own drawbacks and advantages. The development of writing your own data protocol is actually, it's not too hard, but if you never touched data protocols before, it can be quite difficult, but it's also very fast. Network tables is good because it's already there and it's easy to use, but it also has its own drawbacks, like you have to adhere to this certain standard as well. Protocol buffers are great, they're fast, they're very easy to put on, but protocol buffers are actually written in their own little like subset of a language, so it can be quite the learning curve. But take a look at all these options, maybe some more options, and make an informed decision about which one you want to use. Again, this is why the off season is so important for this kind of thing. All this happens over a network over either TCP or UDP sockets. Both of these go through your robot wireless radio to either your driver station or your robot rear. The only difference is that TCP is a session. So what that means is that when you make that connection is going to stay active and it's going to reuse that connection until that connection breaks. So if for some reason your coprocessor goes offline, your robot rear will be notified, the coprocessor is disconnected. I don't know what to do now. The good thing is you do have that session. The bad thing is the packets themselves are quite bigger. They have a little bit more latency to them, but nothing which is really something to write home about in terms of FRC. But you do have that session and you'll have to be responsible for keeping to reconnect that session. The other option is UDP sockets, which is basically just a fire hose of data. It's like if your coprocessor was standing at one side of the field and your robot rear was standing at the other side of the field, and the coprocessor was just throwing data at the other guy. It doesn't care whether that other guy actually gets the data or not. He's just throwing the data anyway, and it's a responsibility of robot rear to catch that data and deal with it. Frames can drop, so you might not get data on the other side, but if you send it often enough, that typically doesn't matter. Like if your failure rate is like 1% and you're sending 30 frames every second, dropping 1 frame every 3 seconds isn't that big of a deal. But it's up to you and how you implement your processor. A lot of this, actually it's kind of a mixed bag. Some of it will work on TCP. If you're using network tables, it'll be TCP. And if you write your own data protocol, you can do it in UDP or whatever you see fit. I've personally had success with both, but I prefer UDP. And I think that's just about it for now. So that's everything all put together. I'll leave a bit of a footnote for further reading. So on this topic of sensor fusion, if you really, really, really want to get into more automated stuff with autonomous robotics, which is great for the first 15 seconds of your match, or here in Australia, when you get to university, we have other competitions like NIARC, which is an autonomous robotics competition. Sensor fusion becomes really, really important because you need to know exactly where your robot is. In our case, we merged a LiDAR, which is the same thing they use on self-driving cars, and a gyroscope and a camera to all try and figure out where a robot is. This is something you'll want to take a look at, sensor fusion. It's something really, really great, and it's like, once you dive in, you're going to realize just how deep this field is. Some keywords to look out for are Kalman filters and sensor fusion and Bayesian inference, and that's about it. Anyway, what I am going to do is that now that all this is done, all the way back to the start, on my website here, In a couple of days, I will post a recording of this session, as well as all the slides, as well as a little bit of references for further reading, if you want to have more of a look at it. So keep in touch. If you RSVP'd to the Facebook event, I'll post it in there also. And yeah, that's kind of just a bit of revision material, or if you want to take a look at a bit more. So I think that's us done. If there's any questions, forward them to the people in charge, and they'll type them out to me, and I'll answer shortly. But apart from that, I think we're all good. Thank you for having me. Okay, so I got a question coming through. Is it possible to track the trajectory of bowls, frisbees, etc.? Yes. The answer is yes and a bit of no. Well, actually, a little bit of yes and a lot of no. So the hard thing about tracking balls and frisbees is that it's hard to tell what exactly a ball and frisbee is. So typically they don't have their own vision tracking targets on them, which makes them pretty hard to see. But even if you can see them pretty clearly, as they're moving through the air, you'll have this bit of motion blur and it'll be hard to make out exactly what it is. That being said, if you have a good enough camera, you can track these. So, for example, I've seen teams create some form of model to try and find the boulders from first stronghold. That's great. You can base it, you know they're round, so you can base it on a shape. You also know that they're gray. They might have a logo on them, stuff like that. And they're fairly easy to track as well. But if you also have a camera like, for example, the Microsoft Kinect here, which has some kind of depth sensor, you can also get kind of how that object appears in space to the robot as well, which is also really easy to identify the target. The biggest problem is identification, but if you want to track exactly where it is, this is where this slide with the better approach comes in. You will need to constantly update your set point of whatever you're tracking, because as it moves through the air, you'll have drag. Your image might not be that high resolution, so you won't be able to tell exactly where it is. But when you track that object, you can constantly refine your guess as to where it's going to go. In fact, if I bring this up real quick, just bear with me for a second. There's actually this really cool video which used a ton of like high-tech gear and a ton of cameras to make a dartboard, which when you throw a dart at it, will always kind of go towards where the dart is. It's made by this guy called Mark Rober on YouTube, and he's an ex-NASA engineer who worked on the Curiosity rover, I believe. So it has a ton of motors on the back, and it will automatically realign to where it thinks the dart's thrown thanks to these little cameras in the corner. So it is possible to track them. It's just really, really difficult. In fact, I don't think I've ever seen a team in FRC do it. But that's kind of a basic answer to that question. Yes, you can, but with a lot of uncertainty, and it's very, very difficult to do so. But good question. If there's any others, forward them up to the front. Okay, so what would be the difference between using a phone as a processor or some other kind of dedicated board. So in this case, I dare say you're saying the difference between something like a Jetson or a Pine or a Raspberry Pi compared to a mobile phone. Good question. A lot of people haven't figured this out because the phone, as far as I know, wasn't used until 2016 to do tracking. The basic, the basic key advantages of a phone is that phones are typically widely available, so you can find them fairly well. In fact, one of your mentors probably has an old, probably not the best performing one, but if you re-image it with like a stock version of, in most cases, Android, and write your own app for it, that's fine. The software for it is really fleshed out, so it's really, really easy to write software for a phone. If you know how to, most of the libraries are already there. If not, you can find them probably pre-made for your phone. On the Raspberry Pi and Pine and Jetson, if you want to run OpenCV, which is the main computer vision software for this, you have to actually download it and compile it yourself, which on the Raspberry Pi is actually like a 2-hour process. So you kind of just sit there, you hit enter, and then you leave it alone for 2 hours. Whereas on a phone, it's probably already there. And the phone has an inbuilt camera, and these inbuilt cameras on phones are typically higher definition than most webcams. And they also allow you to adjust exposure as well, which is a key point. So these cameras here, they're great, but to get an image which appears like this dark with these highlights, you need to adjust exposure. Many cameras will let you do this, but only to a kind of limited extent. Phones have a much wider range for this because when you think about it, when everyone's carrying around a phone, they're going to be taking photos in low light, they're going to be taking photos in sunlight. They need that high range of what they can capture, which makes them really useful for vision processing. In terms of communication with like your Robo-Rio, phones, they're okay, but you do have to disable the Wi-Fi, cellular, and Bluetooth, all because of the competition rules, so that kind of limits your options. Phones also don't have an Ethernet port on them, so you can't plug them directly into the radio. So instead, you need to get a USB cable for the phone, and you can use these certain drivers which you can put on the Robo-Rio, which allows it to communicate with the phone over USB using information just like on a network. Got to keep in mind though, this will introduce extra lag, and you might not be able to push as much data over it. So you'll probably only want to push things like contours and bounding boxes, not an entire image. But, you know, give it a test. Good question. Phones are really good if you have access to them. But if you don't worry. Raspberry Pis come pretty cheap. The cameras you'll find just about anywhere. Yeah, they're pretty good. Like this board here, this Pine 64, cost me $20 US, which is about 25 Australian dollars. And it ran 1080p, 30 frames per second vision tracking, and only used like 50% of the CPU. They're insanely good. So, you know, go out there, see what's available, give it a try, see if you can convince your mentors to let you use a bit of a budget to buy a new processor or something. Or I'm pretty sure like some kid somewhere on your team probably has a Raspberry Pi because they're just that popular. But yeah, if you have a phone, go ahead and use it, or give it a try at least. The off season is a great thing. All right. Any other questions? Okay, is there any advantage of having stereo cameras or multiple cameras? Yes. So one camera is great for if you want to tell what angle a target's at or whereabouts it is. But if you want to refine that guess even more, you can have two cameras which are positioned kind of like your eyes. It's something called stereoscopic vision. So if I see if I can Google an image of this really quickly. Basically, the idea is that you put them slightly away from each other, and you know how far away they are from each other in terms of like centimeters. And using some simple math, you can refine where something is in the frame, and you can also tell through perspective shift how far away it is. So it's kind of like having a depth sensor. I know Team 900, the Zebracorns, back in, or it was either 2015 or 2016, or maybe even this year. They had stereoscopic vision for tracking a specific something on the field, and that allowed them to kind of get a better guess. It also gave them the ability to sense how far away something is, because if you kind of take a look at one far corner of your room and you close one of your eyes, you can't tell exactly how far away something is based on just your vision alone. You can based on context, like how big it is compared to everything else. But once you open both your eyes, it's a lot easier to tell how far away something is. That's one way of using multiple cameras. That's a branch of sensor fusion all in itself. That is one of the most well written about branches of sensor fusion, so you can find a lot of details on it. But in terms of multiple cameras, which are maybe not in stereo, like maybe one at the front, one at the back, one on the side, stuff like that, that really comes down to the game. So in Steamworks, it's not all that useful unless you had like a turreted shooter or something. Same with Stronghold, but for things where you want to be able to tell where things are both in front of you and behind you, using multiple cameras is a great way to go. Some teams who do vision tracking, I believe one of my teams, 5663 this year actually, not sure if this made it into a match, but they would have one camera just for vision tracking, which is aligning up with the peg on the airship, and then they'd have another camera which is not processed at all and just sent straight back to the driver's station and was used as kind of like their eyes on the field. So they'd have the high resolution camera, which is being used for vision tracking to get that really high fidelity, that crisp image that they can process. And then the other camera, they just reduce the resolution a ton, send it to the driver station so that they could see roughly where they are and see around with other robots. So yeah, you can have multiple cameras. They can be arranged differently, like in that example. You can have stereo cameras. It just really comes down to what do you want to use them for. Uh, that's always step one when you're implementing a system like this. Figure out what are my needs, what do I have available, what does the game call for, and do some research and make your final guesses based off that. Cool, good question. Any others? Okay.